All right, so this is example 12.2 from the textbook, from the Sataku Circuits 5th edition textbook. And the problem asks for us to calculate the line currents in the three-phase system. Okay, so what are the line currents? Well, if we go back and look at our YY connection, I had defined the line currents as these currents that are basically flowing through the line, right? I guess just like the single, so between the line that connects the three-phase source to the three-phase load, there are line currents here that we need to calculate, right? And so if we go back, and I also showed that we could calculate that on a per phase basis because we have a voltage source, right? Connection over to a load, and then a connection back via the neutral line, and that creates a circuit, right? And that's what I drew here, just a simplified version of that. I showed that we could very quickly find IA by just taking the voltage, right, across the load divided by the impedance of the load, which, you know, that should be pretty straightforward. So let's go ahead and just do that. And our goal basically here is going to be to find IA, which is going to be this current, IB, which is going to be that current, and IC. And I'll just define all of them as the current flowing down the line, basically out of the sources, right? I think that probably makes the most sense. Could also define them here. They're the same exact currents right here. And I think it's important to note, again, that they didn't even draw the neutral here, even though we know it's there. They didn't even draw it because we assume that this current through the neutral is 0, so we can assume that it's an open, but it's important to draw it for the sake of analysis, I think, so that we can see, oh, okay, I do have a closed loop here that I can, you know, sketch. So let's go ahead and do that. And we'll do that 3 times. So we basically have a source, you know, basically a line impedance, which is the impedance of the actual transmission line, and then an actual load impedance that we're interested in driving. So that's going to be 10 plus J8 ohms, and this one's going to be 5 minus J2 ohms. And then this voltage source here is my VAN, but let me just make a couple copies of this first so that we can create all 3 phases. Not that we need to do this. Again, we could just analyze a single phase and then phase shift our answer, and we'll see that. But this is going to be IA, this is going to be IB, this is going to be IC, right? And so this would be my VAN, my voltage between my A and my neutral, my voltage between my B and my neutral, and my voltage between my C and my neutral. And we see those 3 sources. I draw them as sinusoidal sources, of course, because that makes more sense to me. They're not DC sources, so I don't like to draw them like this. But I guess the reason that the book maybe draws them like this is so that you still have the same voltage polarity for when you need to reference it. But we can just assume that it's almost always going to be the plus on the top and the minus on the bottom. Okay, so let's go ahead and solve this. Pretty straightforward. VAN is 110 angle 0 volts. So let's solve that one. It's going to be IA is going to be 110 angle 0 divided by this impedance here, which is going to be 5 minus J2, right, plus 10 plus J8. Those are in series. So that's going to come out to 110 angle 0 divided by 15 plus J6 ohms. We can always convert 15 plus J6 into a phasor. Oops, 15 plus J6, I put times J6. And I get that this is equal to 110 angle 0 divided by 16.155 angle 21.8. This is volts, this is ohms, and so if I want to get IA, I divide 110 divided by 16.155, and I get 6.81. And for my phase, of course, I'm going to subtract 0 minus 21.8, and I get negative 21.8 degrees amps, and that is IA. Now I could go ahead and carry out this process for IB and IC, or I could go back and reference this table. Note that for the Y to Y connection, it says that for IA, all we need to do is analyze the voltage from A to neutral across the impedance. They're calling it ZY, but that's basically the impedance that we just analyzed. It's the sum of these two, the impedance in my line plus the impedance in my load. And they're just saying, that IB is basically just going to be IA with a negative 120 degrees phase shift. And IC is just going to be IA with a plus 120 degrees phase shift. And if we do the math, that's exactly what we'll see. So we could do the math to prove it. And maybe that's what I'll do in the next video since I have another slide. But we could also just write that IB is equal to 6.81 angle negative 141.8 degrees amps, right? That's shifted by negative 120 degrees because my VBN is shifted by negative 120 degrees. And then VCN is shifted by plus 120 degrees. So I would write that IC is 6.81 angle. Let's see, what is negative 21.8 plus 120? 98.2. So I'm going to have a positive 98.2 degrees there. And so my three phase currents, or my three line currents, which are my phase currents, are given as such. And they're 120 degrees out of phase, just like the voltages are 120 degrees out of phase. And that would be my line currents for this problem here. We basically solved this problem. We found IA, we found IB, we found IC. And that pretty much does it for this example. I guess in the next video, I'll just prove, again, maybe I'll just do real quickly, just prove that this is the case for these two line currents. And then we'll move on to the next example. All right, so I'm going to go ahead and end this video here. And in the next video, we'll just show that this is the case by doing the same analysis that we did here. All right, see you in the next video.